Hello, I'm Mark Unkefer, Executive Director of the Fiber Optic Association, and welcome to Smart Cities, Ubiquitous Fiber and Sensing. This is a webinar that is the product of our FOSA Smart Cities committee that's set up a year ago that focuses on some of the great applications that fiber optic sensing enables, and we'll talk about that in some greater detail. We're very pleased to have our chair and co-chair of the Smart Cities Committee. Giovanni is a senior researcher for NEC Labs America, and Cate McNaught is handles market development for Carnegie Optical Communications. And in addition to their FOSA roles, they both have kind of a distinctive role in technology. Both individually are patent holders. So they're not just presenting great applications, they have been involved in the process of making new technology available. I know we're going to start off with Cate, but we look forward to the presentation from both of you.
Thank you, Mark. Thank you for that wonderful introduction. Good morning, everyone, and thank you for joining this discussion on fiber optic sensing and smart cities. As Mark said, my name is Cate, and I manage emerging applications market development at Corning, and I'm a longtime FBA participant, member, supporter, and just really excited to be here this morning to talk about this. I am joined by my colleague Gio, a senior researcher at the NEC Laboratories and fellow fiber optic sensing enthusiast. And we're planning to share with you what we believe to be some exciting potential coming from this technology and this budding application space. The first portion of our material is context setting, and I'll handle that. I'll take us through a variety of touch points on smart city in general, the technologies that we can expect to see used in them, a general treatment of network trends, and ultimately, really, this is setting up for us why we believe fiber optic sensing may play a role in the smart city of the future. And then from there, Gio will share depth with you on what is fiber optic sensing, how does it work, and how it may be used in smart cities and communities in the future. So with that, we'll jump right in. And Gio, if you could move us forward, please. One more. And we will start with kind of a treatment of what is smart city. And I've pulled together 3 definitions from 3 different sort of thought leadership organizations out there, really to convey a couple of things. One is certainly we can read how these different entities define smart city. For instance, the Smart City Council says smart city is one that has digital technology embedded across all city functions. Okay, so they kind of describe what is it from that perspective. They touch on the human perspective, which is to enhance livability, workability, and sustainability. Okay, that's good, right? That's pretty simple. But you see other definitions out there too. This is one where it says a smart city brings together technology, government, and society to enable the following characteristics, A, B, C, D, E, and moves through again aspects of the human experience. And then another one is smart and sustainable city is an innovative city that uses information and communication technologies to improve quality of life, efficiency of urban operation and services, competitiveness, while again it meets the, again, human needs, right? Economic and social environmental aspects. So I share this to say it gives a sense, these definitions give a sense for this abstract concept, but they don't necessarily deconstruct it into something tangible. They begin that process, but it's to say, if you're sitting here and you're listening to, well, what really is a smart city, and you find that you kind of get the gist of it, but it lacks clarity, then congratulations, you're in great company and welcome to the subject. So with that, what I'd like to do is sort of touch on that and then move into some more specifics in an effort to deconstruct it into something tangible. If you could advance us, please. Thank you, Gio. So here's a listing of some applications that we might expect to see in the smart city. You can certainly see intelligent traffic, Internet of Things. You might imagine that a smart city would have an intelligent emergency response network of systems, right? Like this would be a complex way of managing emergency situations. Public safety would probably be a very high priority that utilizes smart city technologies. You could imagine smart grid, right? The efficient use of energy, telemedicine for those people who need medical discussion but don't necessarily need to go to a specific place. Telemedicine can play that role. Smart lighting, smart transportation, sustainable housing and utilities, right? As you think about urban growth, how can a smart city approach the subject of sustainable housing? Autonomous vehicles, high precision urban models. This is kind of an interesting one. Singapore has something like this, that they take urban planning to a very high degree of precision in a virtual environment. Resilience is a massive topic, and how can the smart city technology offer up resilience to these entities? And then governance. So here's just a list of applications, potential applications. It's not exhaustive, but it's enough to say what might exist in the smart city, and kind of put some of these in your mind. And as we move forward, we're going to pick up how might fiber optic sensing touch on some of these things as well. So that's the application space. We'll go ahead and we'll talk about the participants. Thank you, Gio, because this is one where you can kind of look through and see this breadth of participation, different organizations, entities, what have you, coming together to touch the subject of smart city and smart community. And for me, this is really a depiction of why does it remain fairly nascent, right? Why is this, I guess we could call it a market, why does it remain pre-coalescence, right? At least that's my assessment of it in this region. We do have instances where cities are deploying, of course, and they're trying different things, but by and large, it hasn't quite yet coalesced. And this is one person's perspective on why that might be. It's because we have just a huge number, one aspect of why that might be. We have a huge number of different entities trying to figure out how to contribute, right? How to build a business model around it, how to sustainably come up with value that helps shape that landscape. And so these things are still happening, and different participants are looking for different roles within that ecosystem. So as this starts to work its way out and value creation and monetization of that value creation starts to come about, one would expect increased clarity, right? But here's an example of all the different types of entities that are having a shaping force in the discussion. So we've talked about applications. Here's the list of participants, or some example of participants. We can talk about the types of technologies. And all of this is sort of a backdrop to say, look, it's a complex thing, right? So you can have artificial intelligence type of technology, big data management technology, fog and cloud computing, right? We can see the making of networks becoming very efficient through SDN and NFV. The communications of little devices that are collecting information about their environment and sharing that information up, across the communications network. These are part of that ecosystem of technologies. And then, of course, you have the different ways of communicating wirelessly, right, through Wi-Fi, CBRS, et cetera. And then, of course, ones that a lot of us are very closely familiar with in FBA, which is your various PONs and wireline communications technologies. All of these play a role and have to work together to create that fabric of communications and information management that we believe plays a role in the smart city. So it's a huge topic, right? And if that isn't evident, just through this sampling of applications, participants, and technologies, it is, right? It's a very wide and diverse set of participants and technologies. And so what I'd like to do is use this information and communication technology stack on the left-hand side. This is a kind of a, well, I don't want to be, it's a technological depiction, right, of a system. And what you have at the very top is going to be your application layer. This is where users can come in and find the information they need at their fingertips to make the decisions they need to make on a regular basis. And these things can touch transportation, any application you think of that might want to use information collected from the city. This is what we're talking about. It's where the human beings interface with the data. And beneath that, you're going to have the data and supporting layers, right, that bring that information together. So things like data collection, data processing, using that data and mining it for actual insight, right? It's one thing to have a huge amount of data at your fingertips. It's another thing to be able to use that to some useful end because it's been processed in a way that generates insightful information, right? So that happens. Beneath that even, you have storage and computing, right? So you're going to be collecting that information, caching it, you're going to be housing it. This is basically the repository of where this massive amount of information will reside. And these things are disparate locations. They happen in different locations around cities and urban areas. And then the network layer under that, this is really, I think, kind of the heart and soul. We're starting to get into the heart and soul of the optical layer and the role optics play in the networks that underpin this whole concept, right? So you have those networks that are publicly owned, privately owned, various operators own their networks, municipalities own their own networks, right? So there's those points A to B, right, of connecting this building to that building, this user to that user. It's the optical foundation. We'll talk about that as we go forward. And then finally, the data acquisition layer. So these are the little sensors that are out there in the environment collecting information. It's not enough just to collect it if it can't go somewhere and be used, right? So that's the stack that appears above data acquisition. It has to get collected, transported, housed, analyzed, and used. And that's really what we're looking at. So it's a little bit of a complex thing, right? It's a little bit technical, but what this stack does is it takes an otherwise very abstract concept of smart city and it deconstructs it into constituent components, and you can start to see a relationship between components. And you can see where optics and fiber optic sensing reside within that stack. So moving forward, something that I've kind of tipped my hat to already, if you could move forward one more, dear. Thank you. A quick treatment of fiber underpinning all of this, and what I personally believe will become the foundation upon which smart cities are built is optical fiber. It's versatile, becoming ubiquitous, passive, inert, and thus far we've yet to find its transmission limit. So in terms of its sheer capacity to carry information, it's the limits are unknown at this point, right? So it really is, to use the often overused expression, future-proof. It really gives ample runway, right, for the network of the future. And at its most basic level, it guides light, right, and that light carries information. The reason we're so bullish on fiber is that if you look at what's been driving its proliferation, there's a fundamental limiter here, and I'd like to introduce this chart. It really is brilliant and succinct depiction of information. On the x-axis, you have distance, right? Notice it's logarithmic, so your distance increases tenfold each time as you move over to the right. And then on the y-axis, you have your data rate, gigabits per second, and again, logarithmic, right? So this gigabits per second transmission rate increases tenfold each time you move up a little point on that axis. And you can see that there is, through our study, a fundamental limiter to how much a conductive medium can convey data rate as a function of distance, right? There is a fundamental limiter there, and it's about 100 gigabits per meter per second. So as transmission speeds and distances begin to approach that blue line, it necessarily requires moving from a conductive medium to an optical medium. And that's where we see so many of these applications, and you can see it. You can see it in data centers. You can see it in the access network. It's kind of right there on that line. You You can see it in of course, in areas where they've long been fiber, right? Your metro rings, your long haul links, your submarine links, these have long been fiber. And so you start to see these application spaces kind of cross that line. And the city, right, the access network really is right there on the line and moving to the upper quadrant there, or the upper half of that chart. So that's kind of the why fiber. If you could move forward one more, Gio, I think this really starts to crystallize when we look at some of the major trends. You can see those you see those submarine links between continents, right? You see those massive links between cities. And then in and around cities, of course, as we know, highly fiberized and growing, right? More fiber. And then you see this massive density of fiber in various central offices or head ends or data center locations, right? That's just the breadth of fiber deployment is large and growing. One more forward, please, Gio. And if you look at one of the major trends touching our industry, the need, again, this underpins that transition from the conductive medium into an optical medium. You look at what it takes to achieve some of the major KPIs associated with 5G. You know, you truly are in that area of, okay, it's got to be an optical link if you want to achieve, you know, some selection of these KPIs. And so if you think about the investment moving toward that, right, you think about the deployment of fiber to achieve not just 5G, but advanced broadband, right? You're really seeing just immense investment into an optical foundation. And if you could advance one more, Gio, I'm getting to the kind of the transition here. And here's sort of an image. It's kind of the punchline, right? If you say, okay, you're talking to us about smart city, help me understand the linkage between optical fiber optic sensing, and smart city. You know, I'll give you a linkage between fiber and the city environment, or the, you know, the urban and suburban environments, which is as these technologies begin to drive that transition into the optical part of that logarithmic graph, right? It really is driving the deployment of fiber deep into those environments. And you start to see that optical foundation emerge, the foundation that fiber optic sensing could use, right, to various ends. Gio will discuss some of that with you. But the immense densification of the optical network is what we're looking at and anticipating. So that's kind of that's the formation of the foundation, right, in my mind, around why fiber, why fiber in a smart city, and what with it. So with that, I think that that gives the intro, right, the context setting around fiber and the urban environment. Gio, if you could advance us one more. And I'll hand it over to you.
Very much, Kate. That was an excellent setup. And so to that point, Kate is saying that fiber optics are ubiquitous at every level, even in the burgeoning 5G and broadband investment that's coming in the United States, for example. They're going to be even more ubiquitous, as she showed. And so I want to show here how fiber optics, therefore, can be used for sensing in smart cities as value adds for that coming investment, so that for the existing fiber optic infrastructure and for the burgeoning fiber optic infrastructure, by utilizing fiber optic sensing, you're able to add a lot of value to that infrastructure, and you're able to basically enable a game changer for smart cities. And so let's first ask, what makes a city or community smart? If we look at the Smart City Community Act of 2021, it says the definition of a smart city as defined in the bill says a smart city gathers and incorporates data from systems, devices, and sensors embedded in civic systems and infrastructure. So the key word here is sensors. Sensors are at the heart of smart cities. They are the heart of smart. And so we understand canonical sensors to be things like cameras, microphones, possibly accelerometers, geophones, etc. All these kind of sensors are disparate, but they have many things in common. For example, they all have electronics. They all require electrical power. They all require wired or wireless communication. They are all affected by electromagnetic fields, static or dynamic. They are affected by extreme environments like extreme pressures, temperatures, precipitation. Some of the sensors are affected by visibility, like cameras, whether it's foggy, day, night, etc. Many sensors are affected by line of sight. If you're not directly in front of them, you have a problem. And then for utilizing multitudes of sensors, another issue is their synchronization. You have to sync them all up to get them to work together over the scales of cities and communities. And then in addition, such sensors may have privacy concerns. And then aside from all that, if you want to use these sensors, you have to deploy them. And once they're deployed, you have to service and maintain them. And the ultimate goal is in a smart city, as sensors are at the heart of smart cities, is to sense everywhere, everything, all the time. For example, creating a digital twin from which we could extract value and provide all the things that smart cities need. But as I just described, with all the challenges of sensors, there are kind of too many sensors are required to enable the things that we need for smart cities. If we look at an example, let's look at a highway, Highway 10 from Los Angeles to Phoenix. The highway is over 500 kilometers. If we wanted to sense ubiquitously over this highway, we wanted to use cameras, we maybe would place one camera every 100 meters. This would require thousands of cameras. All those cameras would require electrical power, communication, synchronization, deployment, maintenance, etc. This is a veritably impossible task, and from a cost and also from an execution standpoint. So as Cate kind of set up, however, in the coming 5G and broadband investment in the United States, the existing investment into 5G and broadband, fiber optics are a major component. They are ubiquitous. So the question is, if we already have an ubiquitous infrastructure in cities and communities, which is fiber optics, can we use that ubiquitous infrastructure for ubiquitous sensing? And that's where fiber optic sensing comes into play. So let me walk through fiber optic sensing. Let me give you a definition of what it is and how it can ubiquitously enable smart cities. So fiber optic sensing is basically the utilization of a fiber for sensing. And similar to communication, light is launched into the fiber. But the difference is you don't have to receive the light on the other end of the fiber. You can launch and receive light from one end of the fiber. And as the light travels, it exhibits several physical phenomena. For example, these things called scattering. There are several different types of scattering in the fiber. Sometimes we call them Raman, Brillion, and Rayleigh. And scattering is analogous to why the sky is blue. So the sunlight is white, but when the white light hits our atmosphere, the small particles in the atmosphere scatter the blue light towards our eyes. That's why we see a blue sky. And so basically scattering is a redirecting of the light. It's kind of like throwing pool balls against each other. But in this case, instead of pool balls, it's the photons of the light hitting the small molecular imperfections of the fiber optic glass. And the imperfections cause the light, just like the blue light, to hit the particles in the air and reach our eye, or pool balls to hit each other and go into the pockets of the pool table. In this case, when the light is traveling down a fiber optic, it hits the molecular imperfections, and a small amount, a minuscule, something on the order of a billionth of the light that goes in is reflected backwards towards the beginning. And they can reflect in different ways. Sometimes we call it Raman, Brillion, or Rayleigh. And in the next slide, I'll show you how we can leverage each types of those kinds of scatterings to do a different kind of sensing. But that's happening every point along the fiber at a microscopic level, at a molecular level. And so there's continuous scattering. And basically we can detect that scattering at the beginning of the fiber. And if we're detecting, for example, Raman, and we analyze the changes in the scattering, we can look at temperature changes in the fiber. If we look at, for example, Brillion backscattering, and we look at how the Brillion backscattering changes, we can detect strain changes. And if we look at Rayleigh backscattering, we monitor how the Rayleigh backscattering changes, we could look at things like acoustics or vibration. The benefits of fiber optic sensing are that we're just using light and glass. And also we are, because the scattering is continuous along the fiber, we can sense at every point along the fiber for very, very long distances. Using one centrally located piece of optical electronic equipment called an interrogator, which we place at the beginning of the fiber. And so the only thing that needs electrical power or communication or protection from the environment is that interrogator. The actual optical fiber itself can be deployed as it is, whether it's existing optical fiber or it's new optical fiber. So it allows us to monitor fiber optics from a single location just by injecting light into it, no different than communication. It allows us, therefore, to do it 24/7, 24 hours a day, 7 days a week, continuously, again, over the very long distances of optical fibers, even up to 100 kilometers. And because we are doing this at every point along the fiber, just by plugging in this one optoelectronic device, we are able to sense over thousands of points over one fiber. That enables high resolution, even at a meter or a few foot scale, to be able to localize things like temperature or vibration or strain to within a few feet or a few meters. And again, because we are using light inside glass, this does not require any electrical power along the fiber. It doesn't require any wired or wireless communication along the fiber other than the fiber itself and the light inside, and therefore it's passive. We don't have to deploy it if it's already deployed, as in the telecommunication infrastructure as Cate described. So therefore we don't have to maintain or service it other than what is already maintained and serviced for its use for communication. And again, it has many, many uses, depending on how we look at the scattering in the fiber, depending on how that piece of optoelectronic equipment that's centrally located, the interrogator, analyzes the backscattering. We could, with just the fiber itself, we could monitor temperature, strain, vibration, and even derivatives of those things, such as magnetic fields and other types of radiations. So with one optical fiber, we are able to enable multiple disparate types of sensors. And because we can utilize existing fiber optic infrastructure, such as what exists for 5G or in broadband, we can enable multiple applications over a single system. And additionally, since we're doing this at we're basically plugging in a centrally located optoelectronic piece of equipment at the beginning of the fiber. This equipment can be upgraded easily, whether in software or hardware, over time. And so therefore, there are many different kinds of applications for optical fiber sensing. For example, by placing a fiber optic along critical infrastructure, like a pipeline, we could monitor leaks. We could monitor tapping into that pipeline. If people illegally cut into the pipeline, we can monitor other types of aspects of oil and gas pipeline operation, like pig tracking. We can monitor hot tapping, valve detection, etc. We could also monitor, do things like security and safety. For example, by placing a fiber optic on a fence around a perimeter of an airport, for example, or a prison, or another kind of similar facility. We could actually monitor if someone's crossing that perimeter, climbing the fence, cutting the fence, etc. If we were to bury a fiber in the ground along that perimeter, or even along a national border, we could detect if personnel were walking across the border, if vehicles are driving across or along the border, or if someone was digging or tunneling along the border. In addition, we could, the fiber optics, because again, it's analogous to geophones or accelerometers, we could monitor other types of seismic activity, such as rock falls, landslides, earthquakes. And in the next slides, I'll kind of show you how we can additionally utilize that seismic information to monitor things like traffic flow or the flow of trains or other kinds of transportation. And this is not an exhaustive list, but I won't read everything on this list, but there are a number of different fiber optic applications because of the fact that we can, from a centrally located optoelectronic device that's plugged into one end of optical fiber, for an optical fiber that is as long as 100 kilometers, we can monitor every few feet, every few meters along that optical fiber various things such as acoustics, vibrations, temperature, strain. And so this is not an exhaustive list of all the applications, but maybe you can think up your own application. And all said and done, the point of that for a smart city is that if we leverage the ubiquitous fiber optic infrastructure, for example, in 5G or broadband, we can do ubiquitous sensing over a smart city, which is schematically depicted by this diagram, thanks to FOTEC. We can monitor vehicles driving over bridges. We can monitor the health of the bridges. We can monitor even boats onshore or offshore. We can monitor vehicle traffic along the highways and along the roads of the city. We can monitor perimeters around airports or other critical facilities, et cetera. The point is, because in the existing or burgeoning telecommunication infrastructure like 5G or broadband, because it is, as Cate showed, it predominantly comprises fiber optic or will predominantly comprise fiber optic, we can utilize that existing infrastructure within cities and communities to do various types of sensing by simply plugging in these optoelectronic devices called interrogators at centrally located positions along anywhere along those fibers. So there are many different applications of this, and FOSA, many FOSA members have described such applications from their organization in various webinars. So I want to direct you to the FOSA YouTube page where many of these applications are discussed in length. So feel free to take a look at any of these videos. I believe this is not the total list of videos. There are many, many videos from which you can look at to see the different applications and benefits of fiber optic sensing. And I'll just go through a few now, a few representative examples as it relates to smart cities and communities. So the first example is surface transportation. And many FOSA members have been exploring the use of fiber optic sensing for surface transportation, including my organization, NEC. For example, in 2019, NEC and Verizon utilized fiber optic sensing over Verizon's existing telecommunication network in the United States to monitor traffic along highways and roads along which that fiber optic infrastructure was deployed. So, for example, in the city of Dallas, we plugged in our interrogators, these centrally located optoelectronic devices, to one end of an optical fibers in the city of Dallas. And the fiber optic lengths comprised up to approaching 100-kilometer lengths of optical fiber. And much of that optical fiber was deployed along highways and roads. And so by just plugging in that interrogator, we could see all the vehicle traffic or the vibrations created by vehicles, cars, trucks, et cetera, along the highways and roads, along which the Verizon fiber optic was deployed. We could see all the vehicles. We could detect their speeds, their locations. We could even detect their density, like traffic jams, and we could even monitor the road quality. Recently, we have, my point of showing this slide is to kind of show that this kind of solution for surface transportation monitoring via optical fibers is scaling to a great extent. Recently, we have deployed the same solution for the Japanese network transportation infrastructure called Nexco. Nexco is basically the company that is a government-related company that monitors, that controls all the highways in Japan. And so we have recently deployed the system for Nexco in Japan, where we're utilizing fiber optic sensing to monitor traffic along Japan. And again, the goal is to utilize fiber optic sensing to monitor all the highways in Japan. And again, because it is veritably impossible to use other types of sensors. So for all the benefits I showed for fiber optic sensing, you could deploy this at scale, for example, over the country of Japan to monitor all the highways and roads and all the traffic. Here's another example of monitoring. Here's an example of using fiber optics to monitor resilience. You can monitor pipelines. For example, by placing a fiber optic along a pipeline, you could monitor leaks, or you could monitor if someone were digging or excavating near the pipeline. So this is a slide from FOTEC. You could monitor things like power cable faults. I'll show a short video of the ability of fiber optic sensing to monitor a cable fault. So basically, this is a electrical cable in which an optical fiber is also inside the cable. And so if there is a fault along that cable, for example, if it arcs, you can actually detect the arcing and detect the location of the arcing and the power fault along the cable kind of instantly. And so it's significantly safer to locate these faults and faster and cheaper to repair. And it's very precise, again, because with fiber optic sensing, you can sense every few feet, every meter over many, many kilometers of fiber. You're able to kind of see visually exactly where a fault like this is to within a few meters or within a few feet. And so you don't just have to use existing fiber optic infrastructure. With the burgeoning deployment of 5G and broadband, when fiber optic cable is deployed for communication, you could also kind of think ahead to deploy it such that if you wanted to use that infrastructure for sensing in the future, or you wanted to add to it in the future, you could. And you can do this via deploying the correct cables or the correct conduit. And this is kind of embodied in the dig once legislation, where, for example, the Fiber Optic Sensing Association is working with the US government to say, when you do deploy fiber optic infrastructure for 5G or for broadband, only dig once, deploy that fiber such that you can use it for communication and sensing. So in summary, fiber optics are ubiquitous in cities and communities. The ubiquity of fiber optics can be used for ubiquitous sensing. So when you think smart cities and communities, similar to things like IoT, 5G, and cellular vehicle to X, you should also think fiber optic sensing. Fiber optic sensing, with all its advantages, such as no electrical power, no wired or wireless communication, et cetera, they actually make cities and communities smarter. And there are many applications such as surface transportation, resilience, public safety, environmental governance. So if you have any questions, please feel free to contact the Fiber Optic Sensing Association, myself, or Cate at Corning. So thank you very much.
Thank you very much, Cate and Gio. To ask a question, you can type it in the box that's to the right. Let me start off with Cate. You've done a really great job of describing sort of the transition that technology has taken place. So there used to be a real distinction, sort of separation between wireless and sort of wireline, if you will. And the densification that you've described that 5G drives reflects to this transition to HETNets, to heterogeneous networks, where data can flow from wireless to fiber, and fiber is really essential to be able to enable the advanced technologies across the board. Can you comment a little bit about kind of somehow how that has opened up some additional use cases that might not have existed before, where sort of wireless had capacity limits, and the availability of fiber for backhaul has provided new ways of doing things?
Yeah, I think I'm tracking on the question. I mean, there's a lot of wires in wireless, right? That's an often cited, I don't know, cliche. Those wireless connections are connected to a network with something wired. Increasingly, those connections, which all gets backhauled, all gets connected onto an optical network at some point, especially if those connections are leaving the immediate area and going to another city, for instance, or across the city. So increasingly, those connections are becoming more optical. Certainly between that occurring along with the densification of the wireless access points occurring, the opportunity to collect information from sensors wirelessly is of course increasing too. So is there a fundamental, capacity limiter there? Probably not for your average sensor, right? I mean, a lot of these are low transmission rate devices at the moment, but you start getting into things like high definition cameras, kind of the sensors that are moving video in real time, these things are going to require a little bit more capacity, and I think we're going to see it come online. So definitely that blending, that heterogeneous network blending, the moving of information from one location to another, the management of that information. I think those technologies are all present, right? They're just, to me, the challenge is integrating them, right? And having the right mixture of participants bring a system to life, if you will, that does that effectively. I don't know if that answered the question.
I think that does. I mean, and that is the challenge of being able to bring in the capacity, and that really opens up the next question for Gio. And it was great to hear some of the description of sort of adoption use cases where you have an agency. You mentioned an agency in Japan that was able to integrate the technology. Could you elaborate a little bit on the challenges of getting that early adoption, where you've got a visionary that has the how shall I say, the capacity to be able to implement some of these technologies? That seems to be one of the barriers, where the technology can do a lot, but you need the imagination and the capacity of people to decide to go ahead with it. So you have some thoughts as to how that takes place?
Thank you for your question, Mark. Early adoption is really tough. I think for any new technology, especially at scale, it's very tough for governances to kind of accept it because of the cost and the risk. So I think many FOSA members, including NEC, are working towards to scaling their proof of concepts such that we can prove that the adoption is worth it. So, for example, NEC, for example, if I just speak for myself, we have worked with Verizon at scale over multiple cities monitoring traffic through their fiber optic network. And now we are working with the equivalent departments of transportation in Japan, like Mexico, to use fiber optic sensing to monitor traffic over large scale, many hundreds of kilometers of highway. So those kind of proof of concepts themselves, I think, are going to make it easier for other entities, other departments of transportation in the US to adopt, because when they see it working at scale over long periods of time, then there will be the confidence to kind of use it for themselves. So I think the POCs that the initial deployments that all the FOSA members, like NEC but not limited to NEC, are doing, are going to help to overcome the roadblock of that early adoption.
So the next question is a more granular question, but it is an interesting potential application. Is it possible to implement fiber optic sensing technology to do weight in motion measurement for heavy trucks? So I assume that's an application that involves those weigh stations that trucks have to go through.
Question. I think the answer is it's definitely possible. I think for sure fiber optic experts may say that to quantitatively measure something like that is challenging for some of the sensing modalities, like the use of measuring acoustics with Rayleigh scattering, for example. And there are different ways to sense things, as I showed from the fiber optic. You could measure strain also, or different derivatives of strain, such as pressure. So there are definitely ways to do things like do weigh in motion. In addition to leveraging the different fiber sensing modalities, which have become quite mature nowadays, you can apply artificial intelligence / machine learning to those things, which actually can overcome some of those other roadblocks. So I believe it's definitely possible to kind of combine the existing fiber optic sensing modalities with things like artificial intelligence, machine learning, to do some functionality like weigh in motion, for sure.
Sounds good. So next question, really, it's interesting. It's helpful for sort of the exploring the cross use of various applications. So can rail and pipeline monitor be used as part of a system for earthquake monitoring system?
That's another great question. Yeah, in general, as we kind of showed in some of the slides, by plugging in these centrally located optoelectronic units we call interrogators to one end of an optical fiber, you can basically sense multiple things. You can do different sensing modalities over that same optical fiber, such as monitor temperature, monitor strain, monitor acoustics, etc. And because then you can, you're centrally located, you can apply all sorts of software, artificial intelligence, machine learning to that sensing data in digitally, in software, in artificial intelligence, in machine learning. You can enable multiple applications for one or any or multiple sensing modalities. So for example, if a fiber is deployed along a railway or a highway, while it may be desirable to monitor the trains along the railway or the vehicles along the highway, of course, the fiber being passive is going to receive signal from many other things like earthquakes or construction, etc. And again, using software, artificial intelligence, machine learning, you can monitor all those things and more from the same fiber, even if it's deployed for a given use case. And that's kind of the point that was made in one of the slides, that it is easily upgradable in the future. Should you have another use case, should you want to expand your use case in the future, all you have to do is change something in software, change one centrally located optoelectronic unit to be able to create new and expanded use cases in the future, which is exactly what smart cities and communities, I think, are going to need.
So the next question is a great follow-up, but it's for Cate, which has to do with the use of fiber. So what I'm hearing here, and you can kind of expand on that, is that fiber optic cable that is installed or in place for one particular use can be used for additional sensing applications. That's a question.
It is, yes. In general, the answer is yes. There are cable constructions that facilitate greater sensing, I guess it doesn't insulate the fiber as much, right? That fiber has the ability to interact with the world around it in a more precise way that can translate to sensing applications that are more precise. But the general answer is if there's an installed base of fiber, then it can be used for sensing. If there's a planned investment in fiber, then the opportunity arises for, again, is there a dedicated strand or two? Is there a dedicated cable, right, that goes in there and provides feedback for a specific application that's desired? So I think it's a mix. For me, it comes down to use case, right? If there is an installed base and there's a desire to tap into the information that is able to be extracted from that fiber and use it for some good end, then by all means, that's certainly technologically possible. From a forward-looking view, you would want to probably consider use case. Think about infrastructure monitoring, right? Is that something that you would want a tight relationship between the fiber and its environment, right, to give precise information in that application? So that might be a case where you would deploy a dedicated cable for that application. But overall, if there's a fiber present, yes, we can read light from it and gain knowledge of its environment from it.
So next for Gio, and this is having to do with kind of early adoption, you referenced a couple of organizations that NEC had worked with. So in Japan, it was a road maintenance authority, and here in the United States, it was with Verizon. What are your thoughts as to kind of who are the early adopters? Who drives adoption for smart cities application? Is it cities, or is it telecommunications operators, or is it some combination of the two?
It's another great question. I think it's going to be a combination of the two. For sure, again, as many of the FOSA members are doing these proof of concepts or early deployments or first deployments, those are going to prove, those are done through people like Verizon or Nexco, et cetera. However, these deployments can also be done through governances like at the city, state, or national level. I think they are being done by some FOSA members at that level. So I think it's going to be both. And I think the proof of concept or the early deployment for either of them, whether it's like the Verizons, the Nexcos, or it's the city, state, federal government, I think they're going to kind of, again, it's going to be both of them. They're going to inform each other about the confidence to do this at scale. So I think it's going to be both.
Next question has to do with public safety. Are there some public safety applications that you have worked with, such as this is an example references detecting gunshots and doing sort of gun location identification? Or is that a little like the truck's another one that needs to get explored?
Yes. I believe many FOSA members have worked with many different public safety applications. For example, perimeter intrusion detection, border security, etc. I think the benefits of doing those kind of applications with fiber optic sensing is, again, you don't have to deploy sensors at scale, which require maintenance, service, and then they're affected by environmental extremities like temperature, electromagnetic fields, etc. So for sure, many different safety and security applications, for example, border security and perimeter intrusion detection and others, using fiber optic sensing would prove definitely advantageous because of all those benefits. It's more scalable, requires less service and maintenance, and it's also, you could add on use cases as we just described in the previous question as you go along. So even if FOSA members don't have all the answers today, in the future, we could apply fiber optic sensing to many things because it has that ability.
Thank you. Could you elaborate a little bit about, you've talked about sort of how things are detected, but could you elaborate on the sort of screening or process that avoids for sort of false alarm or false positive information, and how does the software, or how does an operator know that an alert really isn't something that they need to pay attention to?
Again, another great question. So I think about it as you can do that in two ways. How do you avoid false alerts? For example, I'm monitoring traffic along a rail or a highway with fiber optic sensing. I don't want to get a signal every time somebody slams a door nearby or something like this. So how do you do that? And I think of it in two ways. The first way is, well, we always, I think many FOSA members like to make the analogy that fiber optic sensing is like a long array of microphones, one microphone every few feet, every meter, over many, many miles, kilometers of fiber. And that's a good analogy. But actually, fiber optic sensing, if I'm talking about acoustic sensing, is like microphones every few feet. It's also like accelerometers every few feet. It's also like geophones every few feet. It's also like ultrasonic sensors every few feet. Because fiber optic sensing doesn't have the limitations of each individual sensor. You can actually sense over the ranges of all of those sensors. So a fiber optic sensor can be like all of those sensors at every point. Therefore, you can kind of tune in to the kind of thing you want to sense, and you can tune out the thing you don't want to sense, like these false alarms, just by having the ability of fiber optic sensing to be like many sensors. Secondly, you can apply things like artificial intelligence and machine learning to be able to distinguish and discriminate between the things you want to sense, like rail or vehicle traffic, or things you don't want to sense, like a door slamming nearby, etc. And so I think those two things are going to be the way that, and are the way that we're able to get the things we want with fiber optic sensing and not set the things we don't want. And by the way, that's how artificial intelligence and machine learning, for example, work today. When we are, for example, with video cameras, we can tell cats from dogs, but we don't have to pick up cars or something like that.
That's very helpful. Next question has to do with the availability of the presentation, and thank you, Gio, for referencing our YouTube page. But this presentation, of course, will be available on the YouTube page within a matter of hours, if not minutes, after all of this is completed, and is a great resource. Some more information, could you, either you or Cate, provide a little bit background on the FOSA Smart Cities Committee and what it does, and its mission is.
Maybe, Kate, I'll let you do it. I've been
Yeah.
talking too much. Go ahead.
Yeah, sure. Absolutely. So the FOSA Smart Cities Committee, we're dedicated to furthering the knowledge of this technology and what we believe to be its potential applications. We like to bring people together that have a common interest in it, that see its potential and want to work with one another to try to really coalesce this potential, because it is it's not mainstream yet, right? The market's not defined yet, but it is an amazingly powerful technology, and I think with the optical foundation becoming as prevalent as it is, wouldn't it be a shame if we didn't look at it and work together to try to maximize the benefit of it. So that's really our objective, right? To share the knowledge, bring people together, identify use cases, bring them to life, right? Identify value creation potential, and bring the right people to the table to make that become a real thing, so that our industry can leverage it in the way that, the way that it wants to. That's our objective, and we value everybody's insight, opinions, perspective, analysis, and it's a young and dynamic conversation, so please join it.
Well, thank you for that. And as I said, the presentation will be open shortly. We've come to the end of our questions, and so we've come to the end of what has been a very informative presentation. Both Gio and Kate, thank you for both this presentation and all you have been doing with our Smart Cities Committee. So this ends this FOSA webinar.
Thank you, Mark. Thank you, everyone.